Today we want to calculate another line integral. Remember we're integrating a vector field over a one-dimensional curve. The elements that we need are parameterizing the curve and where we're going to plug things in. So the integral of c over c of f dot dr is the definite integral from a to b of f at r of t, where r of t is a parameterization for the curve c from a to b. And dr is r prime of t dt. So yesterday, we integrated 2i plus j over various parts of a circle. And we speculated that if we integrated all the way around the circle, we would end up with 0, which is the case. This leads us to think that a line integral over a closed curve, is that always going to be 0? And so today is about saying, no, not always. It will depend on the vector field over which we are integrating, or the vector field that we are integrating. So both of these vector fields, we integrate over the same closed curve, but we get 0 for the first one, and we'll end up with 9 pi for the second one, assuming, of course, that earlier I did the calculation correctly, which is a big assumption. So I did invoke the word closed curve. Closed curve just means starting and ending point is at the same place. Otherwise, we have an open curve. The other thing that we have here that we're going to want to distinguish is whether a curve is a simple curve or not a simple curve. Simple means it doesn't cross over itself. So here in pink, we have a simple closed curve. Over here in red, we have a closed curve because the starting and ending point is the same, but it's not simple because the path crosses over itself. Over here in purple, we have an open curve. So this curve is not closed, but it is simple. And up here in blue, because I didn't plan on talking about open, closed, simple, not simple, here we have a curve that is not closed and also not simple. P and Q, the starting and ending point, are different places, and the path crosses over itself. It's going to be important for us later on to distinguish whether a curve crosses itself or not. Just by way of inception, if you recall, think back to your definite integrals. And if we have a function that is sometimes positive and sometimes negative, the definite integral calls that the area under the x-axis, calls that negative area. And so you could have some areas canceling out. You could have some areas canceling out. We don't have to worry about that if the function is always above the x-axis. I know I'm not pointing to a function that's above and below the x-axis. This is completely unrelated. Let's calculate the line integral over of this vector field around this curve. So the vector field that we're integrating is 2i plus xj. X we're going to get from the parameterization. Remember, what we're doing is we take the vector field and evaluate it at all the points on the curve. On this curve, x is 5 cosine of t. So the vector field evaluated at the curve will be 2i plus x times j, and x is from r of t. So this is going to be 5 cosine of t j. This is what it looks like to evaluate the vector field at the points on the curve. The orange didn't show up yesterday because we had 2i plus 1j. No x or y showed up there, so it didn't show up. Now, we're integrating all the way around the circle, so t will go from 0 to 2 pi. And we need the dot product. with dr, and dr is -5 sine of t I plus 5 cosine of t j dt. So I've got this dot product of these two vectors. When I calculate the dot product, I will get a scalar, in this case, a scalar function. So let's make that calculation. We are still integrating from 0 to 2 pi. Here we'll have -10 sine of t plus 25 cosine squared. This is a scalar function because we've done the dot product, so I don't need i's and j's anymore. And this is still dt. What's wrong?
Yeah. Well, yeah. You.
Oh, it should be 25 pi. The one I did in my office was a 3. I couldn't remember if I used a 3 or a 5, and I looked it up. See, never trust me. Or did I do that deliberately to find out? No, I just. I'll edit that out later. So in this case, we have to integrate cosine squared. We can be like all the Hughes Hallett book using parts. It's a terrible example for parts, because then we'll start using parts all the time. Better when we're dealing with trig functions to use identities. There's always an identity in a trig function. In this case, I'm going to rewrite cosine squared as a half. I'm going to write this as a half plus a half cosine of 2t. And then I'll multiply by 25. And it's plus, so I can just keep that. So I'm just going to integrate those two terms. So from the -10 sine of t, the integral is going to be 10 cosine of t plus 25 halves t plus 25 over 4 sine of 2t. And we're still going from 0 to 2 pi. Any questions? I don't need the dt anymore. I don't need a plus c because we're doing a definite integral. Those will cancel out. We're integrating from 0 to 2 pi. We can see that since 0 and 2 pi, since cosine and sine will both have the same values at 0 and 2 pi, we can see all this stuff is going to cancel out, except for the 25 over 2 times 2 pi. That's where the 25 pi comes from. Let's watch it happen, though. It's good to know what's going to happen, and it's good to calculate how that happens. Cosine of 2 pi plus 25 over 2 times 2 pi plus 25 over 4 sine of 2 times 2 pi. Minus 10 cosine of 0 minus 25 over 2 times 0 minus 25 over 4 times the sine of 2 zeros. Sine of 2 pi and sine of 0, those are both 0, so we're not worried about that. but the two cosine terms also drop out. Because this cosine of 0 is equal to 1 and cosine of 2 pi is equal to 1. So I got 10 minus 10 cancels out. This term 25 over 2 is 0, and so we end up with 25 pi. The thing that we want to note is that we went around a loop. We integrated this vector field around a loop, a closed curve, and we did not end up with 0. And apparently I closed the window that I wanted. Any questions? The difference in the vector fields is that the first vector field is constant everywhere. And the second vector field, we're seeing different things. This is a vector field that we've looked at before. The vector field 2i plus xj has, in your perspective, parabolas as flow lines, as these parabolas going from left to right as flow lines. I don't have enough space to draw it. I have a wonderful diagram for this example, but this margin is too small to contain it. Any questions, comments, snide remarks? Remember that when we're calculating line integrals, this is just integration, but the multiplication that we're using is the dot product. Applications of line integrals are going to be applications of dot products. Dot product, was that? It all comes back. All we're doing is the same thing. That's why Calc 3 is the easiest one. The thinking is already in play. We know that when we're multiplying and our factors are continuously variable, we have to integrate. And that's all we're doing here. We want to do this dot product, which is multiplication. We want to multiply at an angle. We're not just interested in the product of two magnitudes. We're now looking at the product of two vectors. There's some angle between them. Sometimes that product is going to be positive if the vector field and the curve both match up. So like if the flow line of the vector field is the same as the curve, those are going in the same direction, then our product is going to be 1 times those two magnitudes, cosine of 0. But as the vector field and the curve start pointing in different directions, the product starts to decrease. Questions? Well, the other thing that we want to notice from based on this example is that if we want to make this more complicated, the only thing that's going to happen is when we get to the integrating part. When we get down to here, this part is the only level of difficulty that there is. Well, once the curve is parameterized. Once we have a parameterization, that's step 1. That's the first difficult part. The next calculus difficult part is doing the integration. Any questions? Comments? Snide remarks? All right. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.